Today's session is related to the Unit 3 in the course of Electricity, Magnetism and Electronics. Okay, the title of Unit 3 is Alternating Currents and Electromagnetic Waves and Maxwell's Equations. Okay. Uh, Coming to the contents that are related to the Unit 3 are the introduction to alternating current. What is the advantage of using alternating current over direct current? Then coming to the LCR series resonant circuit and LCR parallel resonant circuit, what is meant by quality factor, what is the comparison between LCR series and LCR parallel resonant circuits, what are the differences between them. Then coming to the Maxwell's equations, what are there in integral and differential forms, and the Poynting theorem. Okay. Coming to the introduction of alternating currents. Alternating current is a type of electric current that reverses direction periodically. Okay? Periodically, it will changes its direction. Okay? LCR series and parallel resonant circuits are important in AC circuits for filtering and tuning. For filtering and tuning purpose, LCR series and resonant circuits plays a crucial role. Okay? Understanding resonance, bandwidth, quality factor and their interrelations is crucial for circuit design. Okay? In order to understand the circuit design, we need to know about the resonance, quality factor, bandwidth. Okay? What is the advantage of using alternating current over direct current? Okay? What makes the alternating current uniqueness? Okay? Using a transformer with alternating current, we can either step up or step down the voltage at our choice. Okay, it's our flexibility to either step up or to either we can step down the voltage. Okay, alternating current induction motors and other appliances are mechanically more robust and electrically simple. Okay, they are very simple. Okay, and they are robust. The line losses, okay, the line to line, what we can say the grid connection losses in alternating power transmission are very low, even over long distances. Okay, over long distances also the losses are very low. The alternating current can be readily converted into direct current when required. Okay, by using rectifiers. By using rectifiers, we can direct convert an alternating current into direct current. In alternating current circuits, the current can be reduced without any appreciable losses of power with the use of a choke or a capacitor. Okay, we can, by using the choke or a capacitor, we can reduce or without any appreciable losses, the alternating current can be transferred. Okay. Coming to the LCR series resonant circuit. This is how it will look like. Okay, LCR series circuit. Okay, L is called as the inductor, C is called as the capacitor, and R is called as the resistor, and this is the it is called as the alternating power supply. Okay, AC power supply. Okay, consider an inductor of inductance cell, a capacitance of a capacitor of capacitance C, and a resistor of resistance R, and all of the three are connected in series and they are connected to a AC power supply, okay, which is having an electromotive force of E is equal to E naught sine omega t. Okay, E is equal to E naught sine omega t. Okay, this is how the circuit will looks like. Okay, all the three, like inductor, capacitor and resistor, are connected in a single chamber and the two in a series connection. Coming to the potential difference across the inductor is given by EL. Okay, E suffix L. The EMF or the potential difference across the inductor is given by EL is equal to L into di by dt. Okay. Where L is the coefficient of self-induction, as we have seen in the second unit, and I is the current that is passing through the circuit. Okay, I is the current that is passing through the circuit. Okay, the potential difference is equal to the product of coefficient of self induction and the and the what do you say, the rate of change of current. The potential difference across the capacitor is given by EC and is equal to the ratio of charge and capacitor Q by C, capacitance of a capacitor. The potential difference across the resistors R is given by ER is equal to R into I, where capital R is the resistance of the resistor and I is the current that is passing through the circuit. Okay. Here we can see that L is the coefficient of self-induction, I is the current that is passing through the circuit, Q is the charge between the plates of the capacitor, okay, C is the capacitance of the capacitor, and R is the resistance of the resistor. By using the Kirchhoff's second law, we can say that EL plus EC plus ER, the potential difference across the inductor, capacitor and resistors is equal to the total potential difference E. Okay, by substituting them we can have the relation. So by mathematical derivations, at the end we will get the maximum current. Okay, by then we will get the maximum current. I naught is equal to E naught by Z, where Z is called as the impedance. Okay, Z is called as the impedance. The impedance is given by Z is equal to square root of R square plus omega L minus omega minus 1 by omega C whole square. Okay, Z is given by square root of R square plus omega L minus 1 by omega C whole square, where XL is equal to omega L and XC is equal to 1 by omega C. They are called as the inductive reactance. XL is called as the inductive reactance and XC is called as the inductive capacitive reactance. Okay? Inductive reactance and capacitive reactance respectively. And the phase difference is given by tan phi is equal to omega L minus omega C by R. Okay, omega L minus omega C by R, where R is the resistance of the resistor. Or you can say that the phase difference phi is equal to tan inverse of omega L minus 1 by omega C by R. Okay. By substituting them in the resonant frequency condition, we will get the resonant frequency equation like F naught is equal to 1 by 2 pi square root of LC. Or you can say that 1 by 2 pi square root of 1 by root LC. Okay, where L is the inductance and C is called as the capacitance. Okay, the current as you can see in this graph, the frequency is taken along the x-axis and the current is taken along the y-axis. A graph is drawn between the frequency and current. This is how the graph looks like. The current increases as the frequency increases until it reaches the maximum current, which is called as the resonant frequency condition. Okay, after reaching the resonant frequency, it again falls down. This is how it looks like. This is called as the LCR series resonant circuit. Next topic is about the LCR parallel resonant circuit. Okay, in LCR series we have connected the inductor, resistor and capacitor in a series combination, but here you can see in this diagram the one branch of the circuit is connected to the inductor of inductance L and capacitor of capacitance R, which are connected in series, and the other branch of the circuit which is consisting of capacitor. Okay, the branch 1 and the branch 2 are connected parallelly. Okay, they are connected parallelly, and these two are connected to a, so what we will say, an alternating current which is given by the potential difference E is equal to E naught sin omega t. Okay. Again, by using the Kirchhoff's first law, we can get the relation to admittance. Okay, is given by y is equal to 1 by z, which is given by r is equal to 1 y is equal to 1 by z, which is equal to r by r square plus omega square L square plus j. J is the current density, omega c minus omega L by r square plus omega square L square. Okay. This is the admittance of the LCR parallel resonant circuit. The resonant frequency F0 is given by 1 by 2 pi 1 by 2 pi. The resonant frequency which is given by F0 is equal to 1 by 2 pi square root of 1 by LC minus R square by L square, where L is the inductance of the inductor and C is called as the capacitance of the capacitor and R is the resistance of the resistor. Substituting all these values, we can able to get the resonant frequency for an LCR parallel resonant circuit. Okay, this is how the graph looks like when you take the frequency on x-axis and the current on y-axis. It is quite opposite of the LCR resonant series resonant circuit. Okay, as the frequency increases, the current decreases. At a point, we will get the minimum current, and from there the current will go on increasing with respect to the frequency. Okay, as a frequency, the admittance is minimum and hence the current is maximum. Okay, current admittance and current both are inversely proportional. Okay, the frequency is called as the resonant frequency. Okay, this circuit is known as the LCR parallel resonant circuit. Okay, coming to the next topic, quality factor. Okay, quality factor is defined as the 2 pi times of the ratio of energy stored to that of the average energy loss per second. Okay, energy stored to that of the energy loss per second. Okay, for an inductor the quality factor is given by Q is equal to omega L by R, capital R, and for a capacitor the quality factor is given by 1 by omega CR. Okay, 1 by omega CR. Now coming to the comparison between LCR series and LCR parallel resonant circuits are, in LCR series circuit the it is independent of resistance. Okay? LCR series circuit is independent of resistance, whereas the LCR parallel circuit is dependent on the resistance. It depends upon the value of the resistor. Okay, the resonant frequency is in LCR series circuit, it is given by F0 is equal to 1 by 2 pi square root of 1 by LC. Root of 1 root LC. Okay, but whereas in the resonant frequency of LCR parallel circuit is F0 is equal to 1 by 2 pi times that of the 1 by root LC minus R square by L square. At resonant frequency, the current is maximum. If you draw the graph between the frequency and current, you can see like this. Okay, as the frequency increases and current will increases, will reach the maximum current. That condition or the maximum frequency, that is known as the resonant frequency. And whereas in the resonant LCR parallel, the resonance current is maximum at you can see it is minimum, where we can see that the current frequency increases, the current will decreases. After that, if you go on increasing the frequency, the current will go on increasing. In LCR series, the resonant, the impedance is minimum, but whereas in parallel, the resonance impedance is maximum. Okay. A series resonant circuit is called as the acceptor circuit, but whereas the parallel resonant circuit is called as the rejector circuit. At resonance, the circuit exhibits a voltage magnification which is equal to the quality factor, but whereas in LCR parallel, at resonance, the circuit exhibits current magnification which is equal to the quality factor of the circuit. Okay. Coming to the next topic, Maxwell's equations. There are two kinds of Maxwell equations, like integral form and differential form. Okay. Maxwell's equations are a set of 4 fundamental equations that describe how the electric and magnetic field interacts. Okay, both how the magnetic and electric field interacts, like E and B. They are formulated by the James Clerk Maxwell in the 19th century. The Maxwell's equations are crucial for understanding the electromagnetism. These equations are crucial in order to understand the electricity magnetism. The Maxwell's equations in integral form describes the behavior of electric and magnetic field over a region of space. Okay, around the conductor, they describe how the electric and magnetic field will interact. Okay. They are expressed as a set of 4 fundamental equations, as I said, 4 in differential form and 4 in integral form. that involves surface integrals of the electric and magnetic fields. The integral form of Maxwell's equations is useful for analyzing the overall behavior of fields in a given region. Okay. These are the four equations that are related to the differential form of the Maxwell equations. You can see that del dot E is equal to rho by epsilon naught, del cross E is equal to minus d by dou B by dou T, where B is the magnetic field. Okay. Similarly, for the integral form also, we can see these are the four equations that are related to the Maxwell's equations. These four are related to the differential form, and these four are related to the integral form. Coming to the last topic, pointing theorem. The amount of pointing theorem states that the amount of field energy passing through unit area of the surface perpendicular to the direction of propagation of energy is called as the pointing vector. Okay. P is equal to 1 by mu naught E bar cross B bar, where E bar is called as the electric intensity, B bar is called as the magnetic intensity or the magnetic field, mu naught is called as the permeability of free space, and P bar is called as the pointing vector. Okay, or we can say that P is equal to E bar cross H bar. Okay. Why? Because we know that B is equal to mu naught into H. If you substitute B is equal to mu naught H, mu naught gets cancelled and you are left with E bar cross H bar. This is known as the pointing theorem.